We have two learning targets in this section. Find the areas of regular polygons and find areas of composite figures. We're going to find the areas of regular polygons today, then we'll do the areas of composite figures tomorrow. This is on page 791. All right, the point in the interior of a regular polygon that is equidistant from all of the vertices is the center of the polygon. As I showed you a couple weeks ago, it's also the center of the circle that circumscribes the regular polygon. A segment from the center that is perpendicular to a side of the polygon is an apothem. Now, that is not me attempting to say possum with a lisp. The word is apothem. Okay? So, if that pops up on a quiz or somewhere, what that's called, it is not possum. I will count that wrong. Apothem. And you've probably never heard of that before. But it's the segment that goes from the center of the polygon and is perpendicular to one of the sides. Now, you can draw an apothem from the center to each side, and they will all be congruent. Okay? So all you need to draw is one of them. All right, now, in the figure at the right, this regular polygon is inscribed in circle P, and circle P is circumscribed about the pentagon. The center of a regular polygon and a radius of a regular polygon are also the center and the radius of its circumscribed circle. So look what that means, okay? There will be 5 places where you can draw a segment from the center to a vertex. Those segments are radii of the circle, aren't they? They are also called the radii of the polygon. So a regular pentagon will have 5 radii. A regular hexagon would have 6 radii. Okay? So unlike a circle, there's not an infinite number of them. There's only the number equals the number of vertices. Okay? The number of radii equals the number of vertices. All right, a segment drawn perpendicular to a side, we just talked about, is called an apothem. And a pentagon will have 5 of those. A hexagon would have 6 of those. Okay? When you put together 2 radii, if that was just a circle and the pentagon wasn't there, we'd call that a central angle, wouldn't we? We call that the central or a central angle of the polygon as well. Okay? And if I then use the apothem, or excuse me, a side of the pentagon as a chord, then the apothem is actually the height of that blue triangle, isn't it? Because it's the length of an altitude. It goes from a vertex perpendicular to the opposite side. So I would be calling this the base of the triangle. That's the height of it. Okay? All right, let's see here. A central angle of a regular polygon has its vertex at the center, and we got that. Its sides pass through consecutive vertices of the polygon, we got that. And then the measure of each central angle, well, let's think about it. All the way around would be 360. If we could make 5 central angles, the measure of each of those central angles would be 360 divided by 5. If it was a hexagon and we could make 6 central angles, the measure of each one would be 360 divided by 6, and so forth. Okay? You with me so far? All right. Let's see if we can identify all the parts. So, on page 795, number 1. This is part of your assignment. Write it down. In the figure, square ABDC is inscribed in circle F. Identify the center. Okay, what's the center? Yeah. A, radius. What's 1 radius? Segment FC is 1. Segment FD is 1. You only have to list one. I'll list them both. And apothem, they've only drawn in one apothem. What is it? Segment FG and a central angle. So angle what would be a central angle? Yeah, but angle F, there's more than one possible angle F. So let's name it with 3 letters. CFD. Then we're supposed to find the measure of the central angle. So the measure of angle CFD, remember how it works. It's 360 divided by the number of central angles you can put in. And the number of central angles you can put in is the same as the number of sides, or the number of vertices, or the number of radii, or the number of apothems. They're all the same. So 360 divided by 4, and that's a 90-degree central angle. All right, so you think we can identify all the parts? We're going to have to be able to, because I'm getting ready to show you the formula that we're going to use to find the areas of regular polygons. All right, so this is on page 792, and I want to show you how they arrive at the formula, and then we're going to use the formula, okay? So it says from example 2, we can develop a formula for the area of a regular n-gon with side lengths S and apothem A. So S is the length of a side. Now it's a regular polygon. So S is the length of each side. All right? And the apothem is A. And remember, you can draw in as many apothems as there are sides, but they're all congruent to each other. So A is the length of every apothem. All right, now, look what we can do. We can divide a polygon up into 1, 2, 3, 4, however many. We can divide it up into triangles is what I'm doing. And how many triangles can we make? Well, the same as the number of sides, okay? In theory, can't I find the area of one triangle? Yeah. And then multiply it by the number of triangles, and that's the area of the regular polygon. You with me? Okay. So the area of the regular polygon equals the area of one of those triangles times the number of those triangles. The area of one triangle is 1/2 base times height times the number of triangles. So the area of that one triangle is 1/2, and then look what a base is. The base of this triangle is one side of the polygon. And they told us to call the length of each side S. So base gets replaced with S. And then look what the height of that triangle is. It's an apothem, which they told us to call A. So height gets replaced with A times the number of triangles. And there are n triangles. So we've got 1/2 times S times A times n. Now, they reshuffle. And they move that there, that there, that there. All right, so all they did was reorder it, and we know that when we're multiplying, we can put them in any order we want to. Here's why they did that. N times S. The number of sides times the length of a side. Isn't that the perimeter? If all the sides have the same length, if all the sides were 10, and there were 8 sides, the perimeter would be 10 plus 10 plus 10 plus, or 10 times 8 would be the fast way, right? So N times S gets replaced with P for perimeter. And that's our formula to find the area of a regular polygon. Area equals 1/2 apothem times perimeter. Area equals 1/2 apothem times perimeter. Area equals 1/2 apothem times perimeter. And let's try a couple. Let's start with number 2 on page 795. Now, draw that triangle on your paper and draw it big like I did. The directions say to find the area of each regular polygon, and we're going to round to the nearest tenth. All right, so they've told us it's a regular polygon. So I know that I'm going to use area equals 1/2 apothem times perimeter, okay? Now, at this point, all I know is that it's a regular polygon and that one of the sides has a length of 6 meters, okay? Before I can find the area, I have to find the length of the apothem, and I have to find the perimeter. Now, sometimes we'll find the apothem first. Sometimes we'll find the perimeter first. I'm going to find the perimeter first in this one because I can find it. I know the length of a side, so I can get the perimeter pretty easily. So I'm going to go ahead and figure out what the perimeter is. If the length of one side is 6 meters, and it's a regular polygon, what's the perimeter? 18 meters. So 18 for the perimeter. But I still have to find the apothem. All right, well, it's going to be a lot easier to find an apothem if I have one drawn in. I'm going to label that A for apothem. Okay. Well, that doesn't tell me much. But what have we found to be so far this year the most useful type of figure there is? A right triangle. So I'm going to draw in a radius of this regular polygon, not because I actually care what the radius is. It's going to make a right triangle and hopefully help me find the apothem. Okay? All right. Now, I'll bet you can guess this. You know how the center of the regular polygon is also the center of the circle that circumscribes the regular polygon? Which means that each side of the regular polygon would be a chord of that circle, right? So if I've drawn in that apothem that goes from the center of the circle and is perpendicular to the chord, besides being perpendicular to the chord, what else does it do to the chord? It bisects it. So, since each side of our regular triangle is 6 meters, and this side gets bisected, that's 3 meters right there, isn't it? So, you need to remember, and it's something that kind of sort of you already knew, but the apothem is going to bisect a side when it intersects it. Because any segment that's perpendicular, that comes from the center of a circle and is perpendicular to a chord, bisects that chord. So that's what's going on. That's why it bisects it. Okay? All right, now, this is a regular triangle. Now, we don't usually call them regular triangles. What's the name we usually have for regular triangles? Equilateral. And what's the degree measure of each angle in an equilateral triangle? 60. All right? That's 60. That's 60. This one down here was 60. Take a guess what that radius does to that 60-degree angle. It bisects it. In every regular polygon, a radius always bisects the vertex angle, no matter what kind of regular polygon it is. Okay? So that's handy to know, isn't it? So that's 30, and I've got the 90, 60, and we have a 30, 60, 90 triangle. See, you thought these were going to go away, but they aren't. Okay? So we've got a 30, 60, 90 triangle, and what we need is the short leg, isn't it? The apothem is opposite the 30. It's the short leg of this 30, 60, 90. We know the long leg because it's opposite the 60. Do you remember? What do you do to the long leg to figure out the short leg? Divide it by the square root of 3. So the apothem is 3 divided by the square root of 3. And now we can get the area. Area equals 1/2 times 3 divided by the square root of 3 times 18. All right. Now, like we've done so often, we're going to attempt to get an exact answer before we turn it into a decimal. All right. I know that 1/2 times 18 is 9. And I know that 9 times 3 is 27. So couldn't this all be 27 divided by the square root of 3? Square meters. So there's our exact answer. Now let's round it to the nearest tenth like the directions told us. So 27 divided by the square root of 3. And I get 15 point what to the nearest tenth? 6 square meters to the nearest tenth. If I was rounding to the nearest hundredth, what would I call it? 15.59. All righty? We good with number 2? All right. So these problems are extremely doable, but they all require some work. Okay? They all do. So be counting on that. Number 3. This time, our regular polygon has 4 sides. So what's a more common name for this? It's a square. So draw that square on your paper. Make it big enough for you to make that right triangle inside of it. You're always going to have a right triangle inside of it. All right. We know that we're going to use area equals 1/2 apothem times perimeter. And neither one of those things are readily available to us, are they? Okay? So, let's make a right triangle. Draw in the apothem. And we now have this blue right triangle. Guess what kind of a right triangle this is? Not a 30, 60, 90. It's a 45, 45, 90. Because remember, the radius always bisects the vertex angle of a regular polygon. In a square, they're all 90-degree angles, aren't they? So that 90-degree angle gets bisected, so that's 45. And the apothem makes the 90. So then that's got to be 45. Okay? All right, so we can get the apothem now in one step. If the hypotenuse of this 45, 45, 90 is 9, what do we do to the 9 to get the leg? Divide by the square root of 2. So the apothem, the leg, is 9 divided by the square root of 2 inches. Well, since this is a 45, 45, 90, if one leg is 9 divided by the square root of 2, so is the other leg. And then remember how we decided that the apothem bisects the side where it intersects? So if that's 9 divided by the square root of 2, that's 9 divided by the square root of 2. Why do I care? Because I'm working on the perimeter. I got to get the perimeter. So what's the length then of one whole side of this square? Yeah, it's 9 divided by the square root of 2 over 9 divided by the square root of 2, which is 18 divided by the square root of 2. All right? If that's the length of one side, the perimeter would be 4 times 18 divided by the square root of 2. Right? 4 sides. So 4 times the length of one side. And what is 4 times 18? 70 what? 72 divided by the square root of 2. So now we have everything we need. Y'all followed me so far? So area equals 1/2 times the apothem, 9 divided by the square root of 2, times the perimeter, 72 divided by the square root of 2. Okay? All right, now, I've got some options here. Let's see. I think I'll do this first. But I'm getting ready to do in 2 lines. You could do in 1. All right? But I'm going to do this. Look at the denominator. What's the square root of 2 times the square root of 2? 2. So I've got the 2 from the 1/2, and then the square root of 2 times square root of 2 is also 2. Okay? And I can either multiply, well, let's just do it. Let's go ahead and multiply whatever 9 times 72 is. 9 times 72. So I get 648. Well, I know that 2 times 2 is 4. So I wonder what 648 divided by 4 equals. Oh, I'm done. I don't have to turn anything into a decimal. And this was in what? Inches. So inches squared. Questions? All right, now, each of these problems is a bit different because, when you change the figure, you change what kind of right triangle you get. The 2 we worked were our special right triangles. Is there any rule that says for every regular polygon, you'll get either a 30, 60, 90 or a 45, 45, 90 triangle? No, you won't. Okay? So you may end up having to use trigonometry to find the apothem or to help you find the perimeter. Okay? Or you might use the Pythagorean theorem if they give you enough information. So the number of sides changes the angle measures, and then the information you start with changes what you may find first. We found the perimeter first on number 2. We found the apothem first on number 3. Not because one way is the right way. You just take it where the information takes you, or you go where the information takes you. Okay? So don't expect these to all be cookie-cutter problems where they're all just alike. They all use the same formula, and they're all going to use a right triangle. Other than that, you've just got to, you got to use the math that you know is correct and work it out and see where it goes. Okay? So here's what you're doing today. On page 795, 1 through 4, 8 through 13, 40 through 43, and 48 through 53.